Okay, I guess it's 5 past the hour, so maybe we can start. So today we're very happy to have Marcely from, let me try to pronounce this correctly if to the best that I can, Avignon University. and uh, and she was a she's a computer scientist and a postdoc researcher at Avignon University, and she worked on a lot of different um, tasks in speech processing, and I think she's best known for unsupervised word segmentation, and which is what she will talk about in this talk. And she, I believe, also recently just got her PhD. And so yeah, so Marcely, the floor is yours. Yes, please take it away.
Thank you so much. Can you see my screen?
Yep.
Great. So not understand English for this
Marcely, sorry to interrupt you.
Investigate to try to pick textures from different kinds of layers. So we have
Marcely, can you hear me?
the the fully attentional model, which is the transformer. We have this older architecture, which is the RNN1, and we have the speech discretization. When I'm talking about speech discretization models, I'm talking about unsupervised models that have no access to transcriptions, and that must produce a sequence of discrete speech units from the utterances, for the input utterances. And for our task, there are two things that interested us. The first one is that we need a model that is able to work in low-resource settings. So we must be able to produce a good discrete representation for audio signal without having tons of data. And the second thing is that we would like a model to be very concise. So the speech discretization models, what they will do is that they will predict a unit, a discrete speech unit, every 10 milliseconds. So in the end, we will have the sequence of units, and when these models predict the same unit for consecutive frames, so the same unit for 10 milliseconds, then the next 10 milliseconds, as these units are repeated, we merge them. So if a model is changing its prediction all the time, in the end, we have a very long representation for that speech, that utterance. Different from that, if you have a model that is quite concise, that it's consistent on its prediction and tends to predict the same unit for longer periods, we will end up with a model that is a bit more concise. But why do we want something that is concise? We want something that is concise because we are basing our segmentation on bilingual alignments. So you can imagine that by having more candidates for the alignment, it's going to be more difficult to cluster these units into words. So due to that, due to the nature of our approach, we would like to be as concise as possible at the discretization step in order to facilitate the alignment and segmentation task that comes after discretization. And then here, the research question that we have is really, does it still work if we replace the true phones by the speech discretization? Can we still accomplish supervised word segmentation using only a very limited amount of audio data? So regarding the speech discretization models, we are going to present results using 5 different models. 3 of them are from the Bayesian generative family. So these models, they are very efficient in low resource settings. The idea here is that they are similar in structure to a phone loop model. Each unit will be modeled as a HMM-GMM, and we have some prior distribution, which is modeled by a Dirichlet process. So here, the 3 models that we use is the HMM, which is a very simple baseline in which every sound can be a unit. Then we have the SHMM, where we start, it's a bit more sophisticated. We start having a prior over the phonetic subspace. And then the hierarchical subspace HMM, or HSHMM, where instead of having one single phonetic subspace, we have several. And then at training time, we can choose from these different subspaces and adapt in order to generate the unit inventory. So these are the 3 Bayesian models that we use. We also investigated neural models, more specifically vector quantization approaches. The first one that we looked at was the VQ variational autoencoder, VQ-VAE. And this architecture is inspired by dimensionality reduction. We have an autoencoder architecture in which we start by having a bottleneck encoder that will give us a set of features representing the audio signal, continuous features. These features will be discretized by the VQ module. And this discretization needs to be good enough in order to allow the decoder to reconstruct the original audio. The second vector quantization model that we use is the VQ Wave2Vec. This model is inspired by self-supervised architectures such as BERT. It is trained with a context prediction loss. We still have this bottleneck encoder. Here is a bunch of CNNs that after that we have the quantizer model that will quantify different portions of the speech separately. And after that we have an aggregator, and we're going to train the network to predict future samples of that audio in the middle of distractor samples. So this is the second architecture. So summarizing, these are the different speech discretization models that we use in order to generate a representation for speech signal. So we are going to train them with only 4 hours of speech because that's everything that we have for Boito. And we're going to try to optimize them in order to generate concise representations. For the VQ-F2VEC, I'm listing 2 setups because we are trying to use 2 different vocabulary settings in order to exploit a bit more the conciseness. So from here, using these models, we are able to generate the discretization that we need in order to train the neural machine translation models. But before showing these results, so for segmentation, I'm going to just comment briefly a bit about how they look like, the representation from these models. So here I have some stats over the conciseness on the left, average sequence length of the representation generated by these speech discretization models. And on the right, I have the length of their vocabulary in number of different units, so how expressive they are. So basically what we see for the Bayesian models is that they tend to be very close to the reference. They usually are very consistent on prediction, so they are quite concise, and their vocabulary is also around the reference one. And when we look at the VQ models, it's the other way around. Even though we reduced a lot of their vocabulary and we intentionally reduced it to an extreme amount for the VQ-F2VEC, we're only using 16 units. Even though we are forcing the vocabulary down, this model is still very inconsistent on prediction time, so we end up having a very high average sequence length. And in order to illustrate it a bit better, we see here 2 speech spectrograms for the same sentence. On top, we see the output of a Bayesian model, the HSHMM. And below it, we see a VQ model, the VQ-VAE. And we can see by the orange arrows, we can see and compare the different discretizations generated. And we see that the one generated at the bottom, the one from the VQ model, it's at least twice the length of the one above. So we can expect that the alignment will be way more challenging to obtain on the second setting, which could result in a worse segmentation. But either way, we have the 6 setups for speech discretization. We're going to pass our speech through them in order to generate the units. With the units and the sentence level aligned translation, we're going to train neural machine translation models. Here, we'll just show the results for the best one from the last batch of experiments. And then once these models are trained, we extract the soft-aligned probability matrices. We segment using them, and we carry the segmentation over the speech domain. And here are our results. Here I'm presenting results only from Boito. It is still boundary F-score results and the average of over 5 runs. I'm including the top line, which is the best result from the last batch of experiments, so using the true phones instead of real discretization. In red are the results for the baseline, the non-parametric Bayesian model. And in blue, we have our attention-based model. So we have the top line on the right, and then we have our 6 steps for speech discretization. And the first thing that we see when you go from the top line to the setups 1 to 6, we see that, of course, we have a drop in performance, and this is expected because now the output is way noisier and sometimes way longer. But even so, we are still able to successfully generate segmentation in very low resource settings. And also, we see that while at the top line, working from the true forms in the language, you were a bit behind DPSEG. Now, on the real setting of speech, working with the output of speech discretization models, we see that you are very competitive against DPSEG, beating it for a couple of different inputs discretizations. And we believe this is because DPSEG force is not trained to deal with noise, while our models are a bit more robust to this noise. And we also, the second thing is that we also have the bilingual information, which help us attenuate the challenge of the tests. Focusing on the different representations, we see that the setups in green, which corresponds to the Bayesian models, These were our best results, in special SHMM and HSHMM were the best ones as input representation for the NMT training. This is not surprising. It showed you that the average sequence length of these models are very close to the to the reference. So if you are able to segment the reference, we should be able to segment something that is similar to that. Different from that, the VQ models, we saw that they were very difficult to exploit for a task. The networks are very inconsistent on their prediction. And so we had to constrain a lot the vocabulary, and this is not really be the best way of dealing with it, because we do need vocabulary of a good length in order to represent our speech. So in the end, what we find is that while these architectures are very good for many things, they are not the best choice for our direct application of this text-based approach. So if one was to use them with this goal, I would suggest some clustering, post-processing, or something else in order to reduce the representation being generated. Finally, concluding, in this talk, I presented our bilingual attention-based unsupervised word segmentation model that works with speech in low-resource settings. And the main inspiration for this approach was computational language documentation. We wanted to take advantage of the translations that we had, align it to the speech. We wanted to incorporate them and build something truly bilingual. In the process, we investigated different speech discretization approaches. We also compared different attention-based NMT models, comparing their soft-aligned probability matrices for as a starting point of our segmentation approach. We found that RNN was surprisingly the best one. We also proposed a task-agnostic metric for ANE. A task-agnostic metric called ANE for assessing quality of the soft-aligned probability matrices. And in the end, by putting everything together in a realistic scenario with only 4 hours of speech, we were able to beat a strong monolingual baseline. And while I did not show here, this trend was also verified in Finnish, Hungarian, Romanian, and Russian. So for concluding, from here, what we would like to do would be the application of self-supervised learning models for low-resource audio processing, because when I was doing this work, when I was finishing these experiments, was when I heard for the first time of the Web2Vec 2.0. So that was the beginning of the SSL models that are now becoming very popular. So now we know that we can fine-tuning multilingual models such as the XLRS on target data. So now we are not constrained on the amount of data that we have in order to generate a rich input representation. So this would change a lot of things in your pipeline. Another thing that would like to do would be leveraging the bilingual information into the attention layer during training. So some sort of alignment bias during NMT training, which was already done on the architecture, on the literature. And we think that this kind of architectures are very interesting. And finally, here we work on NMT, so text-based. So the next step would be going for speech-to-text translation models and seeing if attention is still exploitable in the settings. So that's everything for me. Thank you so much.
Thank you. Thank you for the great talk. We sort of lost you in the middle for a bit.
I'm not able to listen to you. I don't know why. Can you try to?
Not exactly sure what's going on. Hey, what's going on here?
Let me try and plug my phone. I think I'm still not hearing you.
Oh, so people can hear me actually.
I'm sorry, I'm not able to listen to you. Are you able to? to hear me, I hope, because I just did a 45-minute presentation. Okay, I'm the only one that cannot hear you then. So maybe, I don't know, should I try to re-enter the room? Give me 1 minute. I was able to hear you before. This is strange. Okay, I'm just retrieving the link for accessing the talks. Then I'm gonna reconnect in order to see if this bug will go away.
Okay, okay.
So sorry about this. Okay, 1 minute. Hello?
How about now? Can you hear me?
I can hear you. That was very weird. I'm sorry about it.
Okay, no worries.
Oh, the thing is that I lost all the messages that were in the chat because I had to close the window.
Yeah, no worries. I'll read it out for you. So yeah, there are a few questions. So we actually missed you in the middle a little bit when you discuss the attention mechanisms, and I think also I think we started to hear you back when you compare RNNs, CNNs, and transformers. So okay, so let me just no worries, no worries. It's actually not a whole lot actually, yeah. And so let me just quickly read the questions from the audience. One is, are the different attention-based models controlled for the number of parameters? I believe you talked about this, and I think the answer is yes.
Yes, we try to make them as comparable as possible. In number of trainable parameters, we also try to keep constant things like embedding size and other settings for training, such as batch size. So they should be the most comparable as possible, but it's never exactly the same thing, right?
Okay, and then the next question is VQ wave-to-vec pre-trained in English? And if so, did you try to train them, well, did you try them with English data?
Yes, that's the thing that we did not do at the time. When we were doing this experiment, it was not clear for us if we could indeed do some sort of cross-lingual training with these models, the self-supervised learning models. And since then, we now know that yes, we can, and that is very good. So the results that I showed is of a very low resource VQ wave2vec that I reduce a lot the parameters in order to train with only 4 hours of data in Boshi. But yeah, if I was, the next step now would be using wave2vec 2.0 and use those large multilingual models. Then you can just pre-train and warm the network with some hours of Boshi.
So if I understand it correctly, you train it from scratch. Is that correct?
Yes, I trained from scratch. It was not very long because I reduced the architecture a lot because I didn't have a lot of data.
Yeah, that makes sense. Any more questions? Well, I actually have one myself. When you're doing this translation in order to get the attention map, you decided to go from, wait, if I remember correctly, translating words to phones. Is that right?
Yes.
That's a little bit unconventional. Can you explain the rationale behind that?
Yes, it is actually because when you are building the subline probability matrices, you are computing context vectors for each target token. So we wanted the probability to be over the word candidates in the translation, and not, we didn't want to have a probability for a word in the translation to all the phones. We wanted to have the other way around. So that's why we shift the architecture. Our first experiments we did try to do on the other sense, of course, phones to words. And then what we saw is that many of the discrete speech units were ignored because you do not have the constraint of the probability, the distribution of covering all of them. So that's why we shift. There is some work in the literature that instead of shifting, they constrain the attention mechanism to go on both senses. So you have a distribution over all the words and phones at the same time. But this was a bit worse because this forces to use all the words in the translation. And due to different features in languages, sometimes it is better to be able to ignore some of the words and just concentrate on others.
I see. So it's more like converting a many to one problem to a one to many problem, or is it the other way around? But yeah, but I kind of get it now. Okay. Any more questions?
But yeah, I hope you didn't lose a lot of the talk. I don't know what is this.
Yeah, it's a little bit laggy, but then I sort of caught a bit like here and there, but yeah, and then missed a little bit here and there as well. So it's not terrible.
Oh,
No, it's not
okay.
terrible.
Well, I just changed work computer, so I think I might have some driver problem on Ubuntu that I need to solve.
Well, okay, great. Well, I suppose if people have more questions, feel free to email me or Marcely. And
Yes.
yeah, and so thank you so much for the talk, and thank you so much for joining as well. We will have 2 weeks from now another talks on segmental CPC. So looking forward to that, and I'll see you in another 2 weeks. Thank you all. Bye.
Thanks a lot for having me. Bye bye.
Bye bye.